So welcome to Madison's Chemistry. In this video, we're going to be going over Michaelis Menten Kinetics. So to start off this video, I wanted to just do a brief introduction so that we can understand why we're measuring what we are. So we're first going to look at this graph right here that compares the observed rate versus the enzyme concentration. And as we can see, there's a linear relationship between enzyme concentration and reaction velocity, which means that this is actually going to be the rate determining step, because if we change the enzyme concentration, we know that there's going to be a direct change linearly or proportionally in the reaction velocity. So this is deemed not as interesting, right? It's not very interesting, it's just linear. We know that as we increase enzyme concentration, the reaction velocity is going to change. So now let's go ahead and look at the substrate concentration versus reaction velocity, and we'll see this hyperbolic shape. And it's already a little bit more interesting, because what we can see here is that the enzyme is saturated with substrate up here, right? Like it's got so much substrate that adding more substrate is not even changing the rate, so it's saturated. So we can see this leveling off point. Right? So this is actually pretty interesting, because when we have a hyperbolic, we know that we can normally take some inverses and generate a straight line, which is what we're going to be doing pretty soon. So this hyperbolic shape also implies the binding effect. Okay, so this is basically what we're going to be looking at the entire time. So focus on this. Okay, so now let's go ahead and scroll down and look at what Michaelis Menten is actually looking at. So Michaelis Menten is very similar to what we just saw up there. So we've got substrate concentration, same thing, and then here we have V naught. So instead of just the reaction velocity, it's V naught. So that's going to be the initial velocity of the reaction. So it's the initial velocity. So it's before much product has formed. Okay, perfect. So this is obviously not the most easy thing to look at, right? Because it's in a hyperbolic form, right? So hyperbolic form is an ideal. So let's generate graph in y equals mx plus b format, because it's easier to work with. Okay. So that's what we'll do. And then we'll end up with this Lin-Weaver-Burke plot. Okay, so we'll get a line something like this. And so this is going to be -1 over Michaelis Menten constant. This is going to be 1 over Vmax. The entire x-axis is 1 over substrate concentration. And this is all, the y-axis is now 1 over V naught. And our slope equals Km over Vmax. So you're probably thinking, hold on, where did Km come from? Okay, so let's take one step back. So what about Km? So if we were to look at a curve like we had up above here, let's just redraw that. Okay, so we want some way to be able to measure the affinity So this is substrate concentration. Okay, so the point where V naught is like 1/2 V max is something that we're going to mark. So let's say it's about here. And whatever this concentration of substrate is, that is what our Km is going to be. And that's a Michaelis Menten constant. Okay? So a small Km, or small, I guess should be underlined, indicates a larger affinity for the substrate. Which makes sense because that's basically saying that less substrate is required to have the same V naught half max. So if it was actually here that got it to V naught half max, that's even a higher affinity because less substrate needs to be present, which means that the substrate has a higher affinity for the enzyme. So that's what Km is going to teach us. So let's go back up here. So this is our Lineweaver-Burke plot. It's going to come in very useful for many different calculations that you'll encounter over the course of dealing with enzyme kinetics. So we're going to pick up with how this varies for competitive inhibition, non-competitive inhibition, and uncompetitive inhibition here soon. But this is a good introduction, and I think it gives you an understanding of why we actually use this plot, the Lineweaver-Burke. And it's because we generate so many things. So we generated Km, which we just figured out tells us the affinity that the enzyme has for the substrate. We also, it allows us to plug in our Vmax, which we can't really find in a curve like this because it's just going to be leveling out at some asymptote, right? So it actually gives us a value to solve for this Vmax when we do 1/. So that's why we use this Lineweaver-Burke equation. Yeah, so stay tuned for the next video. I hope this one was a helpful introduction.